And we're recording. All right, cool. Um, so I couldn't sleep last night at like 1 a.m. So I decided to go ahead and make this video, the next video, and I got done, sometime around 1 a.m. and it didn't record. So yeah, it worked out great for me. So now I'm redoing the video. I'm gonna do questions 3 and 4 for 2015 today. Um, and I'm actually going to do 5 and 6 as well. And then all of spring break is going to be dedicated to doing 2016. So you can do that at your own pace. And I'll have that posted for you on Monday. And we can just kind of go ahead and begin. And we'll start 2017 when we get back from spring break. Okay? All right. So I'm trying to keep the audio good, keep good position. Here we go. It says, so number 3, 2015, it says that Joanna jogs along a straight path for 0 to 40 minutes. Joanna's velocity is given by a differential function v. All right, so it's a chart problem. We've seen this type before. We says it's going to be velocity and it's a differential function. Okay, so those are helpful things to note. Selected values of v of t are given in the chart. And measured meters per minute are given. Okay, so it's all given in the table above. So part A says use the data in the table to estimate the value of v prime of 16. So the derivative of velocity, which we know is acceleration. It wants me to estimate the acceleration at time equals 16, which isn't on the chart, but it is right here directly between 12 and 20. So if I want to estimate an instantaneous rate of change on the chart, remember it's just going to be the slope between the 2 points. So v prime of 16 is approximately equal to v of 20 minus v of 12 over 20 minus 12. Which is 240 minus 200 over 20 minus 12, or that's 40 over 8, which is 5, and the units of measurement is acceleration, so we know that's going to be meters per minute squared. Okay, so there you have it. There's A. It's just same. It's a very common part A with a chart problem. That's just estimating rate of change using the slope formula. Okay. All right. Let's look at part B. B says using the correct units, explain the meaning of the definite integral. All right. We got the integral of 0 to 40 of absolute value of v of t in the context of the problem. All right, guys, we've seen that notation so many times. Absolute value of v of t is speed, and we know if we integrate that, absolute value means it's going to be the total distance. So that's literally all it is total distance. It's just testing that you know that. Okay, so if I want to explain that in the context of the problem, so 0 to 40 absolute value v of t dt. All you gotta do is state something about how it's total distance, and you want to put it in the context of the problem. So you want to use the correct measurements and kind of say what's going on. So say something along the lines of is the total distance. All right, so we'll go ahead and state it's the total distance that Joanna jogged. We should probably go ahead and say in meters. Go ahead and put it in context. In meters. And that's going to be from time equals 0 to time equals 40 minutes. From time equals 0 to 40 minutes. All right, so it's the total distance that Joanna jogged in meters from time equals 0 to 40 minutes. Yeah. All right. And now the second part of part B says, well, okay, well, we know what it means. Now we're going to approximate this value using a right-Riemann sum with 4 subintervals indicated in the table. See, that works out because we got 1, 2, 3, 4 rectangles there. Okay. Now, here's the only difference is whenever we've done right Riemann sum, we've never done it with absolute value before. Okay, anytime we've like used Riemann sum to estimate, it was always approximating displacement, or like an accumulation of distance. It never talked about like a total distance before because we've never done absolute value. So in this case, all we have to do is if we have any negative velocities, they have to become positive velocities. We can't have the negative kind of make us backtrack a little bit. Okay. And in the past, the displacement was the same as total distance because we've never really had negative velocities like this value in our chart before. So let's see kind of what's going on here. Okay, so this is going to be the integral 0 to 40 absolute value of v of t dt is approximately equal to. So if I have 4 rectangles, I'm going to have 4 products here. And the first one, the rectangle is a length 0 to 12. So I'm going to have 12 times, and then since it's right Riemann sum, we're going to do the right value. So that's going to be 12 times 200 plus the distance from 12 to 20 is 8. So that's going to be 8 times 240, the right value, plus from 20 to 24 is 4 times. Now instead of negative 220, that's going to be positive 220 because we're doing absolute value. And then plus the distance from 24 to 40 is 16 times 150. All right. So this is calc inactive. I think honestly, if you leave it that way, it'll be fine. The answer key did simplify it down to the way. So if you do simplify, just be careful because they will count your final answer as your final answer. And if you messed up throughout that process, you could get it wrong. But it does simplify down to 7,600 meters. Okay, so there you have it. That was part B, the context of the problem and the approximation using right Riemann sum. And C, so now we're talking about some different person. Instead of Joanna, we're talking about Bob, and he's now riding his bicycle along the same path. And he's doing this for, looks like 0 to 10 minutes. Bob's velocity is modeled by some equation, t cubed minus 6t squared plus 300. Where t is measured in minutes and b of t is measured in meters per minute. Okay, find Bob's acceleration. Find Bob's acceleration at time equals 5. Well, in part A, we had to estimate Joanna's acceleration, but here we don't have to estimate it. We're given an equation. If I want to know the acceleration at time equals 5 and I'm given velocity, this is simply just saying take the derivative and plug in 5 because the derivative of velocity is acceleration. So I'm going to say b prime of t, we'll start off with finding that, is going to be 3t squared minus 12t. So that's the derivative. And now all we have to do is just plug 5 into that, and we got our final answer. So part C wasn't terrible at all. Okay. If I plug 5 into that, that's going to be 3 times 5 squared is 25, minus 12 times 5, which is 75 minus 60, or 15. And this is acceleration, so that would be meters per minute squared. Okay. So wow, I mean, part C wasn't terrible at all. Hardly any math to it. We just had to take the derivative and plug in 5. Okay, cool. All right, and lastly, part D. It says, based on the model from part C, so that B of t equation, it says find Bob's average velocity during the interval 0 to 10. Okay, average velocity. It's like saying find the average value, and we know an equation for the average value. It's 1 over b minus a times the integral of it. So we're going to say 1 over 10 minus 0, which is just 10, times the integral 0 to 10 of b of t, which is t cubed minus 6t squared plus 300 dt. Okay. So this is not calc inactive, so we actually have to integrate this ourselves and go from there. So this is going to be 1/10. Okay. And then the integration is going to be 1/4 t to the 4th minus 2t cubed plus 300t, and we're doing that from 0 to 10. Okay. All right. And if we plug 0 into that, it's going to cancel everything out. So really, all I got to do is just plug in 10. So if I do that, I'll do it up here. We're going to have 1/10, and that's going to be 1/4 times 10 to the 4th, which is just 10,000, minus 2 times 10 to the 3rd, which is 1,000, plus 300 times 10 is 3,000. Okay. Now, again, this is Calc inactive, so leave it that way. I'm sure it's fine. It's all kind of simplified out enough, I think. But if you do simplify it further, let's see, that's 1/10. That's going to be, I think, 2,500 minus 2,000 plus 3,000, I believe is correct. And that would end up being 3,500 divided by 10, or just 350. Again, we're talking about velocity, so that's going to be meters per minute. So there's your average velocity for Bob from Part C. Okay. So this chart problem wasn't too terrible. It's just kind of recollecting a few formulas and concepts, and the math wasn't too bad. Excuse me. All right. Here's the answer key to it, so you can kind of look over that. We got that we have the approximation. We got that. It was just 5 meters per minute squared. It looks like it didn't count off for having the correct units, but I would still always put those. The correct explanation had something dealing with total distance, meters, 0 to 40 minutes. Okay, you need all those things. Write Riemann sum, and notice how they made 220 positive. And then the correct approximation. Again, if you left it right here, I think you're going to be fine, but they simplified it all the way down to 7,600 meters. Part C, the fact that we found the derivative, 3t squared minus 12t. So, and then the answer, just plug in 5 into that. And then D, we got a point for the correct integral, taking the correct antiderivative, and finally getting the answer of 350 meters per minute. Okay? So not a terrible problem. All right, let's go on to question 4. And that is, I like this problem. We finally got just one that is purely a differential equation. Starts off with a slope field. We haven't had one like that yet on our review. So I think this will be a good one. It says on the axis provided, sketch a slope field for the given differential equation at the 6 points indicated. So I only see 6 points. We only have to do 6 points. And all they're grading is just what you put on that graph. But if I'm ever dealing with a slope field on the final exam, just to be sure, I always like to put a chart with all the slope values, just in case they have a hard time interpreting our dash marks. They might refer to this. So I'm going to put xy. I'm going to put dy over dx. Okay, and the 6 points are 0, 2, 0, 1, 0, -1, 1, 2, 1, 1, and 1, -1. Okay, so those are our points, and if we plug those x and y values into our differential equation, all right, what I'm getting is -2, -1, 1, 0, 1, 1 is 1, and 1, -1 is 3. You can pause the video and test those out if you like, but yeah. All right, so let's start off with 0, 2. Over 0 up 2 is -2, so it kind of looks like that. Okay. 0, 1 is -1, so a little flatter. 0, -1 is +1, so a little bit like that. 1, 2 is 0, so we need to have a flat line. 1, 1 is 1. And over 1, -1 is 3, so it needs to be really steep, like that. And that's it. That's all you have to do. So chart and then plot those slopes. Okay. We like slope fields. We get excited when we see those. All right. Now part B. Part B says, okay, well, you got the first derivative given. Let's find the second derivative. We're going to find the second derivative in terms of x and y. And then we're going to use that second derivative to determine the concavity for all solutions for the given differential equation, so all solutions, when we're in the second quadrant. We don't know what the concavity for any solution I have to the differential equation in quadrant 2. All right. So let's first start with the second derivative. d2y over dx squared is equal to, well, we just take the derivative, right? So that's going to be 2 minus dy over dx. And if I want to get this back in terms of x and y, I need to plug in the original dy over dx. So that's going to be 2 minus 2x, and when I distribute the negative, it's going to be plus y. Okay, so that's my second derivative. Okay, now it's saying if I integrate that and I get a solution, no matter what the solution is, okay, I'm in quadrant 2. What's the concavity always going to be? Okay, give a reason for your answer. Well, let's think about the special case of being in quadrant 2. That means that x is always going to be less than 0 and y is always going to be greater than 0. Okay. So if that's the case, think about what happens if you plug those values into this differential equation. Any negative value that you plug in for, say, x, it's going to be a negative times that negative 2, which is going to make it a positive. And if I plug in any y value that's greater than 0 in for y, that's going to be another positive y value. So that's going to be positive plus a positive plus a positive. No matter what I plug in, it's going to be a positive answer. So this is always going to be greater than 0. Okay, and that's your reason right there, is that the derivative, the second derivative, is always going to be greater than 0 in quadrant 2. So you can say it's going to be concave up for all solutions in quadrant 2 because, I guess I can write because, d2y over dx squared is greater than 0. Okay, there you have it. The second derivative wasn't hard to find. You just had to kind of put a little bit of concept behind there, a little bit of thinking to figure out why it's going to be concave up for all solutions. Okay. In part C says, okay, we're going to have a particular solution, f of x, to the differential equation, and it's going to have the initial condition. It's going to have the additional condition that f of 2 equals 3. Now, at f of 2 equals 3, so at the point 2, 3, is that going to be a relative min, a relative max, or neither? And justify your answer. Okay. Whenever I'm discussing relative min and relative max, there is 2 ways to do it. There's the first derivative test, which is the one we always use, or the second derivative test, which is the one we don't use as much. First derivative test says plug in a point. Okay, if it equals 0, if it's a critical point, we're good. And then we're going to test values to the left and right of it, see if it's positive or negative, negative, positive. Then we can classify, oh, it's going to be a relative min or relative max. But in this particular example, I think the better example to use is going to be the second derivative test, because we found the second derivative in part B, and we're given the first derivative in part, well, at the beginning of the problem. Okay, so we already have both derivatives, and it's more helpful to do the second derivative test, because when I'm testing points to the left and right of x equals 2, I have a y value here. I don't want to mess with x and y. So I think the second derivative test is the best thing to do here. Let's refresh ourselves on what that says. Second derivative test says, all right, if we have some value, we'll call it c. If f prime of c equals 0, so if we have some critical point, all right, and that same point, if it makes my second derivative greater than 0, so if it's positive, that means it's concave up, which means we have a minimum. If my second derivative is less than 0, so concave down, we're going to have a maximum. Okay, and that's the second derivative test. So we start by classifying the critical points and then testing those in the second derivative. So that's what I think we should do. So let's start with this point right here. Let's start with plugging in our first derivative and seeing if it's actually a critical point. All right, so dy over dx, I apologize. Okay, sorry. So dy over dx of, I'm going to plug in 2 comma 3 is equal to 2 times 2 minus 3, which equals 1. So right off the bat, the point 2, 3 is not a critical point. This does not equal 0. So if we have a point that does not equal 0, if we have a point that's not critical, then it can't be a max or a min. So we're going to say that x equals 2 is neither max or min. And your justification, if you justify your answer, is this work right here saying that the first derivative equals 1. It's not a critical point. Okay, so there you have it. Not a min or a max because it has to be 0 for the derivative. All right. Okie doke. Let's go on to part D. And then part D says, find the values of the constants m and b for this equation here, y equals mx plus b. That's going to make that a solution to the differential equation. All right, let's think back to when we did these types of problems. If this is a solution to the differential equation, okay, that means that if I take the derivative of this equation here, it's going to be equivalent to this derivative up at the top. It might be in different forms, but they're equivalent forms. Okay. So if I want to find m and b, I need to figure out the values that's going to make this derivative equivalent to this derivative. So let's start off by finding the derivative of mx plus b. So if I do that, dy over dx is equal to the derivative of mx plus b is just m. All right. So I'm saying that this derivative and the differential equation that I got at the beginning of the problem, those are going to be equal. Okay, so I need to figure out what values is going to make this true. Okay. All right, so what I'm going to do is I'm going to say, all right, well, 2x minus y is going to equal m. Okay, I'm going to figure out how that works. Now, the rest of it is just math, so we're going to have to figure out how to computationally solve this. So, okay, I know that y is equal to mx plus b, so I'm going to go ahead and substitute that in. I'm going to say 2x minus mx, and I'll go ahead and distribute the negative to make it minus b equals m. All right. And now, actually, the way to solve this is going to be very similar to the way of thinking we do with partial fractions. So let's go up here. I'm going to start by getting all of it by itself. So I'm going to say like 2x minus mx minus b minus m equals 0. Okay. And here's the cool way to solve this is if you notice we have two values here, 2x and negative mx, that are x values, and we have two constants here. So let's group those together real fast. Okay. So like 2x minus mx is the same thing as 2 minus m x's. Okay. And my constants, I can say this is minus b plus m. Okay. So we have 2 minus m x's and we have b plus m constants. Well, if this quantity has to be equivalent to 0, remember how we did it with partial fractions sometimes when we had to solve for like coefficients? We said, all right, well, there's actually 0 x's and 0 constants on this right side. So that means that 2 minus m x's has to be equivalent to 0 x's. So you can say 2 minus m equals 0. And that b plus m constants has to be equivalent to 0 constants. So you can say b plus m equals 0. We can solve those two. Like for instance, this first one, m equals 2. And for this one over here, we can substitute 2 in for m and say b plus 2 equals 0, or b equals -2. So there you have it. Those are two constants, m and b, that we need to have, that if I were to have, so if I had y equals 2x minus 2, that is a particular solution to the differential equation 2x minus y. All right. That's it. That's all we had to do for number 4. So just kind of checking our work right here. I mean, we had the correct slope field. They only graded it a point for where it was equal to 0, so right here, and a point where the slope was equal to 1, so here and here. I don't know that. Just make sure it's all right. Okay. The second derivative, we got that right. Okay, it was 2 minus 2x plus y. And then our concave up with a reason. So the fact that we're in the second quadrant is going to make the second derivative always greater than 0, and therefore always concave up. For C, we considered the first derivative at the point 2, 3. We got that it was equal to 1, which is not 0. So then our conclusion with justification. Therefore, there's neither a minimum or maximum at x equals 2. And then lastly, the fact that we found the derivative of our particular solution, and we recognized that that had to be equal to our differential equation. So that was 2 points right off the bat. That the rest of it, so from here down, that was all just worth a point, finding that answer. Okay, it's more so recognizing the fact that the differential equation had to be equivalent to the derivative of a particular solution. All right, well that does it for questions numbers 3 and 4 for 2015. We will do 5 and 6 here shortly, and that's about it. We'll do 2016 all next week and for spring break, and you can just do that at your own pace. Okay. All right. Good job, guys.